Hello and welcome back to the final session of the Bay Area Battery Summit. It's been such a treat to have you all here for the last couple of days, hosting our first virtual BABS, as we call it, with Lawrence Livermore National Lab. It's been wonderful working with them, and we'll do some thank yous in half an hour as we wrap this up. But for now, with not too much fuss, I want to introduce the man I've been calling Stan the Man all day, Professor Stanley Whittingham, who is coming to us live from New York and is the director of the Institute for Materials Research and the Material Science and Engineering program at Binghamton University. But you probably know him as the winner of the Nobel Prize in Chemistry in 2019. And he won that. I looked up the record for the pretty simple matter of the development of lithium-ion batteries, because as I understand it, Stan's early research in the 70s, when I was still in nappies, was the intercalation of lithium into titanium disulfide atoms, and that resulted in all the things, the laptop batteries, the Walkman, of course, initially, and now the EVs and the energy storage on the grid that we've been talking about so much today. So with no further ado, it's my great honor and privilege to have the closing keynote presented by Professor Stanley Whittingham for the Bay Area Battery Summit of 2020. Thank you. Over to you.
Thank you very much. I'm coming from upstate New York, from a snowy day. I hope it's a bit warmer out there. So I want to talk to you a little bit about where lithium-ion batteries started, some of the issues we had then, and in a sense, how much easier it is to do battery research and commercialize today. So I show you some of the applications underway right now. You all know about renewable energy, and I'll finish with that on the last slide as well. One of the big areas that's having an immediate impact is electric vehicles. And I show you a range here from the two-seater that my wife and I rented in Bermuda just over a year ago to two electric vehicles from Britain that the British ambassador took to Stockholm in December. You'll recognize a Jaguar on the left-hand side and a London taxi on the right-hand side. So Britain is very serious about going electric vehicles. Then I show you two much larger vehicles on the right-hand side. This is a 16-wheeler, then a garbage truck. Obviously, a garbage truck is ideal application for batteries because it's stop-start and lifting and lowering the whole time. So some of you not quite my age may not remember that the US postal fleet in Cupertino, California went electric maybe 25 years ago under a DOE program, highly successful. But at the end of the program, they had to give all the vehicles back. So one never understands quite why they didn't do it. These two trucks I show you here by Peterbilt, and these were at their test track just north of Seattle in Washington State. And I should at this stage thank the US Department of Energy, who have supported my research from the beginning. And most of the research I'm doing these days is in team research, either fundamental science through the Energy Frontier Research Center, and these are all the characters involved. San Diego in California, Santa Barbara, and earlier we also had Berkeley involved. And then the more applied effort, the Battery 500 consortium that is run out of Pacific Northwest National Lab. So let's just look at where the future is. I think it's extremely bright for storage and for lithium-ion batteries, and they're ready to go, I think. The big plus right now, the energy density keeps improving every year, and the cost keeps decreasing. So I show you some data from Bloomberg a few months ago showing every year the cost is dropping, and they anticipate that's going to keep going, and this has some implications for the future. The next generation of lithium-ion batteries is probably going to be lithium metal and maybe solid state, and again I'll come back to that. There are many other storage technologies which we shouldn't forget. For long-haul trucks, it's quite possible that you're going to generate clean hydrogen from solar and wind. So you're going to have recharging stations on the interstate highways so trucks can go coast to coast as they do now, or from Northern California to Southern. It's not realistic to think batteries alone are going to do that, though these trucks will have a large battery. And clearly for very large storage and seasonal load shift, pump hydro is still the way to go if you're allowed to build anymore. New York State has a large number of these. I gather California does too. For highly repetitive, high power uses, supercaps still has a place. And later on, I'll discuss recycling. We've got to get this going in an effective manner, and we've got to eliminate toxic materials. Otherwise, we'll get stopped by local communities from building batteries and using them. So let me just go back to the beginning and give a few additional thanks. Exxon in 1972 agreed to initiate a fairly large program in lithium rechargeable. We'd come up with some ideas. I went into New York City to meet with a committee of the Exxon board, and what they call an elevator speech these days, I think I had 5 or 10 minutes with them. At the end of that, they decided to fund a large effort in rechargeable batteries, and they were interested in electric vehicles at that time. So they hired a manufacturing expert from General Electric, development team, and then spent the next 10 years developing lithium-ion batteries. And I show you two of the products. One is the paperweight at the top here. This is what they gave away to potential customers. This particular one is sat right next to me right now. It was built in the mid-70s and is still working. The only bit that's failing is the display. At the lower right-hand side is a large battery, about 6 inches by 4 inches by about 1 inch thick. And this was used to turn a motorcycle headlamp on and off for a whole week at the EV show in Chicago. So electric vehicles were big in the 70s. This was partly due to the gas crisis in 73. So let's just look at a bit of the history, because this tells us where we came from, where we're going, and what we need to do. So we started in 1972, 73, and this is Exxon. We used lithium metal as the anode. We used titanium disulfide as the cathode, and this is a layer structure as shown on the right-hand side here. And all you're doing is moving lithium ions in and out of the structure without changing that structure. And that's what we mean by intercalation. So you intercalate an ion into a structure, just like you intercalate February 29th into the calendar every 4th year. So it's a totally reversible reaction. When Exxon went commercial, they went to lithium aluminum alloy as the anode because they'd already had issues with dendrites with the lithium. Lithium aluminum is very brittle. It lasts maybe 10 or 20 cycles, and that was enough for the testing they were doing in those days. But it was really Akira Yoshino in Japan who then came up with the idea of using carbons to store the lithium. And I show you in this picture, this is graphitic carbon. The challenge here is you need 72 grams of carbon for every 7 grams of lithium. So it's very poor from a weight basis, and the anode takes up half the volume of the battery. So it was with this carbon, and by that time, John Goodenough, who had read our paper on TiS2, was looking at magnetic behavior of cobalt oxide, decided this had the same structure, and he then developed this as a battery whilst in Britain, and the Atomic Energy Authority owned the patents on this material. Subsequently, most of the cobalt has been removed and replaced by nickel and manganese. And in the case of Tesla, they use nickel, cobalt, and aluminum. So this is the commercial system. And it was really in 1991 that Sony had the first commercial success. And I emphasize the word success. There are a number of ventures between 1972 in 1991, including Exxon's, which went commercial but were not a financial success. From 1991 to today, there are clearly a huge number of manufacturers of these batteries. The real issue today, if we're going to get higher energy density, we've got to get most of the carbon out. And a stepping stone to going back to pure lithium, which is really the holy grail, is to use tin or silicon. Both these react with over 4 lithium ions, so have a energy density on a volumetric basis the same as lithium. On the cathode side, I already mentioned the mixed metals. John came up with lithium iron phosphate, and that was in vogue for a long time, is still probably the dominant cathode in China, and I think it's going to come back, and I'll get back to that in a moment. And we have work going on in Binghamton on the manganese analog of that. This is 4 volts versus the 3.5 volts of iron. And on the research stage, we're basically saying we've got to get more lithium in per transition metal if we're going to use these safe phosphates. So we're looking at these vanadial phosphates. So let's just look at this in more of a linear form. So we started out with titanium disulfide. The first really large commercial operation was by Moly Energy in British Columbia, Canada. They used molybdenite, which is a naturally occurring ore there. They made thousands of cells. Number of these caught fire and caused real issues. So they eventually got out of the business and sold it and went to a graphite anode rather than metal. I've already discussed these cathodes. On the lithium side, graphite is, say, dominant, but some of the Japanese companies are making, I would say, very high rate, safe batteries using lithium titanium oxide or lithium niobium oxide. When this is combined with lithium iron phosphate, you've got basically a 2-volt system, but very long lived. So the real issues with high nickel NMC, which is dominant, we'd like greater safety. Clearly, everyone wants lower lifetime cost. And the big advantage of this system, it's flexible. So you'll find out most of the lithium ion grid storage uses NMC today in trailers. And these trailers can be moved from place to place as the utility needs them. So they can go from substation to substation and from state to state. I've already described that lithium iron phosphate is the most stable cathode. It should be the lowest cost. I'm not sure it is right now, but it's much lower energy density. Hence the desire to put 2 electrons or 2 lithium ions into this structure. We've tried this with iron. It doesn't work because the redox potential of iron is about 5 volts, and that decomposes the electrolytes. So a question people always ask, why did it take so long from our idea in 72 to successful commercialization in 91? Mainly because in 1972, everything was new. We had to invent all the components, the anode, the cathode, the electrolyte. Even then, we had to build ourselves cyclers. There were no commercial cyclers on the market for lithium batteries. What most people forget today, there are really no computers for experiments. There's no theory, there's no DFT at that time. So you did everything really by hand. There was also a big lack of advanced characterization. So where today you can easily go to a synchrotron and look inside the battery and see what's happening, you couldn't do that then. There was a lack of a market pull. So we had a technology push, but not all that much of a market pull. And there's a lengthy learning experience. So Exxon learned on lithium dendrites. Moly Energy learned some more, and they had numerous instances. So that's why I think there's only one commercially available lithium battery using lithium metal, and that's the Bolloré cars that come out of France, and they use a polyethylene oxide electrolyte and operate about 80 degrees centigrade. Today, everything is in place. There's a huge market pull. It's possible to have drop-in technology. So if you've got a better cathode, the anode and the electrolyte and all the ancillary material is already there. And clearly, global warming is demanding a solution. So let's just look at what the big guys are doing and where the gaps are. So if you look in all the big companies in the battery space, this includes all the Asian ones, Tesla in this country, the nickel content in the NMCA is increasing. A few years ago, it was the equal amounts of nickel, cobalt, manganese. It's gone now to 60% nickel. And this is mostly because it's the cobalt price driving the cost of the cathode. So the fewer amount of cobalt there, they can cut the cost substantially. Clearly, there are also other child labor issues that driving this. And the goal is to go to 80% nickel or higher. The challenge here, the 80% nickel is much more reactive. The material itself has to be handled in an inert environment like a dry room. You can't handle it in an open lab, even in California. So the question today is, how low in cobalt can we go? And clearly, I think we can probably get to 5% without any trouble. Question is, can we get down to 1 or 2%? And all these materials have a certain amount of aluminum in there. Tesla was using about 5%. Can we get down to 1%? And there are indications we can. Every bit of aluminum in there, you cut the energy density. And there are indications that other materials like magnesium or manganese will be just as effective. And a big question that's been raised in the last year is, what is the highest capacity compatible with getting more than 1,000 cycles with these layered oxides? Jeff Dahn says it's 210 milliampere hours per gram. This is because above that, the volume contracts a lot, so the material tends to crack. If it cracks, then you get new surface that reacts with the electrolyte, and you lose the electrolyte, and your capacity retention is very poor. Let me show you where we stand now on these NMC materials. And this is data out of the Battery 500 consortium. This is this one down here. And this is run out of Pacific Northwest National Lab. And this is work headed by Jay Xiao, an ex-PhD student of mine. And this is with the 60% nickel material in this meatball morphology. So in this consortium, we all use the same material. This particular 60% nickel came from EcoPro in South Korea, and we found it to be very good. And what they did was build these pouch cells. This one is a 2 ampere hour pouch cell, and you can see they've achieved 350 watt hours per kilogram. This uses a pure lithium anode and a new electrolyte in here, and it's achieving 350 watt hours per kilogram. And I should emphasize that this is a real capacity. So we get the capacity from the electrochemistry and the weight and volume of the actual cell. So everything is counted. The volumetric energy density of this particular one is about 700 watt hours per liter. And the testing, cells were built in Pacific Northwest National Lab, and they're tested at the Idaho National Lab. So third-party testing, so totally independent. So as I said, NMCA still dominates, particularly in the US. I expect that the olivine will regain market share. For several years, the olivine was used for grid storage, and there's a facility in Binghamton that used olivine from A123. This is lower cost, but I said it's lower energy density. but safety is a big plus here. And what we're trying to do is develop these 2 lithium phosphates. And I think this will get more R&D attention. And I'll show you on the right-hand side here, this is our data on this vanadium phosphate. So you get one plateau just under 4 volts. So this is vanadium 5 to vanadium 4. Then another one for vanadium 4 to vanadium 3. And you see we get about 305 milliamp hours per gram out of this, as compared with about 200 out of the layered oxides. There are still some issues here, but you can see this is 50 cycles, and the 50th cycle is in fact better than the first. So we've got proof of principle that we can stuff 2 lithium ions into a lattice without destroying it. The big challenge for any new battery technology is that it will have to surpass the energy density and the cost of lithium-ion batteries. And as the cost keeps going down, then any new system will have to get better and better. And I'll mention in a moment, the second life for spent batteries is unlikely. So let's just look at some challenges and opportunities for research, development, and I'll include engineering in the manufacturing space. Right now, essentially all the cathode materials, whether it's a layered oxide, whether it's lithium iron phosphate, is a multi-step process. Tends to be 2, 3, and 4 steps. We need a one-step process to cut the costs. It would also cut the time. We need to include the doping and coating, which is we have on most of these cathode materials, into the manufacturing step. And Nano One out of British Columbia claim they can do this. I've not seen any third-party data yet. But this initial manufacturing needs to include the artificial SEI. Right now, there's a lengthy break-in process where all the cells are cycled 3 or 4 times. This can be over a 2-week or longer period. So this takes a large capex for the buildings. And other areas where we need improvement is lower cost starting materials. Most of the NMCs use nickel sulfate. And if you've got high nickel, for example, 80%, you have to use lithium hydroxide. We need to go back to the mine and look at the supply chain from the mine to the customer and see where we can intersect at a lower cost part of it. We also need thicker electrodes so we can get rid of, say, half the current collectors and separators. This will need better ion and electronic conductivity in the raw materials. And there's a number of other issues coming up. Almost all the cathodes use the organic solvent NMP to make the paste. This is about to be banned in Europe, and I expect if it's going to be banned in Europe, it'll eventually get banned here. And the question, is there a solvent-free method for making the cathode? Right now, the graphite anodes use an aqueous system, so it's much easier to handle, less toxic, and less need of recycling. So we need to look at this. And really the big issue, we need new electrolytes that are non-flammable. The electrolyte really hasn't changed much in the last 30 years. And when you see fires in lithium-ion batteries, it's really the electrolyte that's burning, and it may be initiated by the cathode or something else, but it's the electrolyte that gets the fire going and keeps it going. So let's look at some innovations in the battery space. Where might small companies get involved and have a chance of going? I think solid state cells, it may take 10 years before they're of any significant size, but solid state cells could be alpha and beta tested in things like laptops and phones. There's a range of companies from small startups through some as large as Toyota getting involved in this space, but there are ample opportunities for everybody. The major challenges here really two. One is the electrolyte and its interaction with the other components. It could be ceramic, a nice polymer, or soft inorganic. If it's a hard ceramic, going to have interfacial challenges that have to be solved. I said Bolloré in France is making batteries, or they make the cars the batteries go in using a lithium anode, a PEO polymer electrolyte, and lithium iron phosphate as the cathode. It operates about 80 degrees centigrade, and if you're in Indianapolis, you can rent these cars by the hour. They're not got much of a range, but they do work, and it's really a test bed, but I don't think most people want to operate at an elevated temperature. If you look at the two big areas of solid state, Eric Waxman at University of Maryland is pushing the garnet-based system very strongly. He appears to have some very good results using NMC, sulfur, and going back to titanium disulfide, where they can operate at very elevated temperatures. But right now, because these are ceramics, I believe, is using a liquid on the cathode side, so you got a good contact between the solid electrolyte and the cathode. In most cases, if you've got a ceramic electrolyte, the contact between that electrolyte and a hard cathode will break after a few cycles because they will have thermal expansion issues. QuantumScape in the Bay Area is clearly very well funded, and they will be giving a presentation on their technology at the New York BEST meeting. I think it's December the 8th this year. So you'll know more about what they're doing. They're going to tell us more of the technology there. And then the other big issue with solid state is, what is the cost of manufacturing? The present lithium-ion batteries using roll-to-roll technology is extremely low cost, billions of batteries made each year. So I think when solid state comes in, it's going to have to go after the high-end products first before going into the large devices. At the other end, if you look at opportunities, you look at niche markets, and maybe the Prussian blue effort that came out of Stanford. It's very different from what most people are doing. It has a low energy density. It's claimed to have a very long life, so it might serve some niche markets. So let me just emphasize as I finish, battery manufacturing takes up a lot of energy. There's no point in doing it unless this is clean, renewable energy. And the cathode is the most energy intensive. So the European companies are planning to make their NMC in Scandinavia. There's 3 different companies, including BASF. They each are working in a different Scandinavian country, and they're using hydropower, completely CO2 free. The question is, if we start building many gigafactories in the US, where is the best place in North America to do it? And as we go into large-scale batteries, we have to consider North America, not just the US, because things like nickel, lithium are quite abundant in Canada, much more so than in the US. And batteries must be recycled. A second life is, I think, very unlikely. The economics just don't make sense. If you look at this plot I showed you before, the prices are dropping dramatically. So if you bought a battery in 2010, if its life is, say, 8 years, it's already lost most of its value. So what are you going to be able to sell it for? Maybe $80, not much more than that. So I think everything is going to get recycled. We need clean recycling in most of the components. The valuable area here is, once we get many gigafactories, there's a significant waste from the manufacturing process, so we can have clean recycling there. Then at the other end is the old spent batteries, which will have good material in them or good minerals in them, but may need completely breaking down. And what a lot of the recycling researchers are saying is we need to design the batteries for recycling. This may be just a dream because the battery manufacturers want life and energy density first and foremost. And there's a big issue right now about can we have fluoride components in the batteries because of the PFAS generated when we break down the batteries at the end. So that's an issue that's coming up. And just to conclude, I think the 2020s are going to be the decade of energy storage. It's going to help us clean the environment and mitigate global warming. And between the two of us, we have the two states which have the most demanding clean energy mandates. Those in New York are on the books. We have to go, I think, to 50 or 60% clean energy within the next few years. And we have to have more than 3 gigawatt hours of grid lithium battery storage or similar storage within 5 years. And similarly, 3 gigawatts of wind power in the same time period. And it looks like the wind power, they're going to hit that target well before the deadline. There's a huge push here. And I'll just leave the comments here from the Nobel Prize that we owe our children and grandchildren a cleaner legacy. So we need to all work together on that. So I will stop sharing here and answer any questions you might have. Thank you very much.
Well, thank you very much. That was a fantastic overview of the state of the art in lithium battery technology, where it became. I like your comments on Moly Energy. I'd have to comment that was one of my first scientific jobs working for that company. So there's been a number of questions. I'll start it off here. What current innovations, tools are you most excited about for accelerating the lithium-ion battery research?
I think that the theorists can help guide the experimentalist as to what to look at next, rather than us trying to try everything. So they can calculate for us before we do it what the voltage is going to be, how fast the ions are going to diffuse, whether we have a chance. But I'm not sure they're going to predict the next material. You still need some chemical intuition for that. But no, on all our teams, we have theorists and modelers working with us as experimentalists. And clearly all the big machines you have at Stanford and Berkeley, Argonne and Brookhaven are key to really understanding what's happening at the electrodes.
So a question from the audience. Where do you see, or can you comment on the developments of the future of cobalt-free batteries?
Well, it's clearly going to happen. No, if for no other reason, there's cost to get the cobalt out. And most of the cobalt is in the Congo. So the challenge there, and I think the Chinese own most of that now. There's a cobalt mine, I understand, in northern Idaho, which people are trying to start up. But all the indications from our work, Jeff Darn's work, Dr. Sun's work in South Korea, we probably don't need more than 3 to 5% cobalt in the layered oxides to make them work. And if we can get down that low, maybe 1 or 2%, but cobalt does help in capacity retention.
So for young researchers that are just entering the battery field, what advice would you give them for targeting their research for the highest impact?
Do something different from what everybody else is doing. Don't jump on the NMC bandwagon, or for that matter, on the sulfur bandwagon. I think sulfur is a huge challenge. Battery 500 is looking at it. I would say totally new ideas, like the Prussian blues were new. I would say even looking at the manufacturability of how do we make batteries, we have to leapfrog the Asian technology. That's now 30 years old now and hasn't really changed. If we're going to have a battery industry in the US, we need to do it differently.
So it took 2 decades for lithium-ion batteries to go from concept in the lab to commercialization. So as a community, what do we need to do a better job to move the process forward?
I think today you've got the industry and the markets on your side. They all want better energy storage. They want it lower cost. They want it smaller. No, they want to put a megawatt hour in their pocket, I think is what they'd really like. And I think particularly in California with all your fires, I think most people would like to have, let's say 100 kilowatt hours in their basement or their garage for when the power goes down. And I think we're going to see that happening a lot.
Absolutely, I see it already happening. My neighborhood was close to the fires, and they're picking out people to sort of say, okay, would you be willing to be a test scenario to have like a particular set of battery systems in your house so you can power the pumps in the more rural areas to fight the fires?
Yes. And this was the same issue in New York City after Francis hit them. They had gas in the gas tanks in the gas stations, but no electricity to pump it out.
Yeah. So another question from the audience. When do you predict lithium metal will make it back onto the market, and what will that take? A loaded question.
I think I'd say I've got to be careful here because battery 500 is looking at lithium metal. I think we're going to see it probably go into solid state cells in things like your iPhones, some of your laptops, the smaller devices. I think it's going to be a while before it will go into electric vehicles, into grid storage. No, the end user is going to be still jittery. They still remember or read about the lithium fires from Molly Energy and issues that Samsung had, and some of the issues that the 787 had. And most of those, I should say, were bad designs. You can't blame it on the chemistry, but no, if something goes wrong, you've got lithium metal there, it's an issue. And if you've got a sodium battery, it's even worse.
Absolutely. So do you see promise in technologies beyond lithium ion? Which do you think are the most viable in both the short and perhaps longer term?
Well, no, if you want low cost, you're going to try to go for sulfur. It will have double the energy density and a weight basis of lithium ion. It's going to be much worse on the volumetric basis, so it's not going to go into any mobile devices. There's going to be some, I think, sodium ion for maybe grid storage, but again, the energy density is going to be lower, so it's not going to go into any portable devices. So it's going to be tough for anything to beat lithium ion or pure lithium and something for portable devices. And, you've got lots of things bubbling up in the Bay Area, and that's really where the center of invention is these days.
So another question from the audience. Do you think the consumer electronics, cell phones, tablets, will eventually go away from lithium cobalt oxide?
Not so long as people want longer and longer duration phones. No. This was an issue that came up, I think, 5 or 6 years ago. We were at a meeting and there was an Apple representative there. And we asked him, what's more important? Battery lifetime or better electronics that don't use so much energy? And he wouldn't answer. But it's clearly the electronics have got vastly better. People will remember laptops you couldn't put on your lap because they got too hot. And there's no issue there. So I think you need devices that don't waste the energy. It's the same with data centers. They use as much electricity cooling the data center as they do for all the electronics in the data center.
So since I'm at the National Lab and you've mentioned the Battery 500 and the roles that the labs play, as well as industry pull, can you comment on the most effective ways the labs can interface with industry?
We have to have teams, and the teams, I think, have to involve academia, the national labs, and industry. The challenge we find working with industry, they won't tell you what their real problems and challenges are.
Yep. So in your very long career with many firsts, have you seen, or what type of partnerships have you seen that have had the most success in your teams?
Well, no, the research end is no question that I would say these energy frontier research centers, which are not very big, they're now 3 to 4 million a year. They seem to be very effective at a size where you can manage them. I've got to say the hubs, I think, are too big. They spend more money managing than doing. And I think, some of the national labs, you have these, you call them craters with industry, and some of those seem to be working well. As I said, it's always difficulty to get the industry to really tell you what their challenges are. But I'm a real champion of team efforts. When I worked for Exxon, our groups were about 5 or 6 people. Each one was slightly different in their discipline. So we'd have physicists, inorganic chemists, material science, organic chemists. With a team like that, each one of them looks at a problem in a different way. So if one can't solve it, the other one might do.
And they also seem to have their own unique languages. So communications is always a fun challenge.
So I tell all graduate students and undergraduates, you may be a chemist, but you better understand the language of the physicist and or the engineer. So those are folks you're going to be interacting with.
So perhaps a two-part question on how things are going to evolve. So reflecting on the commercialization process that you've seen in the lithium-ion batteries, and many other technologies have sort of failed, what lessons learned and advice would you have to share with the next generation of researchers and innovators who are trying to commercialize their technologies?
I think we have to get a supply chain and industry involved in North America. We can't keep relying on the Chinese to make it. I know a lot of the battery efforts, even in the Bay Area, they go to China to actually manufacture the batteries. In the end, we have to follow the example of what the Europeans are doing now, where they're basically getting the whole supply chain within Europe, making the batteries in Europe, and making them really where they're needed, near the auto companies. So, initially they were going to build the batteries in Poland and Hungary, and they've decided, no, it's better to, even though the cost may be slightly higher, to build them where the auto companies are, for example, and then import the cathode materials from Scandinavia where the cheap electricity is.
Mm-hmm. So that leads to the second part, and you've touched on this a little bit, but I'm intrigued. So originally, you saw Moly Energy. A lot of the manufacturing capability for lithium ions and technology was developed in North America. It's been shipped to Asia. What do we have to do to get it to come back to North America and California?
Well, basically, I would say all the science and know-how is either American or British. Because I say cobalt oxide came from there. Mm-hmm. All the patents are there. So we have the know-how. We have to stop licensing all our technology to the Asians and basically do what a few companies are doing, insist to begin with that the government buys American. So the military had to, in fact, in the end, go to Asia to buy cells, even though they made the batteries in this country. Some of the bus companies are buying the cells from Asia and building the batteries in this country. So I think we have to do everything here. It may cost a bit more to begin with, but in the end, it will be much more effective. And I think it doesn't matter really what the technology is. We need it homegrown. We need to be in a situation where no one else can control our future totally. And right now, it can be done.
So I think you're saying that the strength of North America, England, is innovation. That perhaps we push the innovation to what's sort of the next generation, and use that as a stepping stone to renew North American manufacturing, or is it more than that?
It's that in part, but I think one of the real issues is Wall Street. Wall Street wants a profit tomorrow, not next year. So companies in the US are less willing to spend, say, 3 to 5 years and invest millions of dollars to make a profit 5 years down the road. So we have to change that culture. I don't know whether that means we need tax incentives to do it, but that culture really has to change. Because in the end, Exxon licensed the lithium battery technology to the Japanese.
Well, it's been a pleasure talking to you, and I know the people, there's been numerous questions here, both through chat and through various devices. It was fantastic that you were able to sort of wrap up our final keynote for the Bay Area Battery Summit. And I thank you for giving us a tour de force of the history of the lithium-ion battery. I really enjoyed it. Thank you very much.
Thank you all, and I hope you had a great meeting.
Yes, we did indeed. Thank you, Professor Whittingham. Truly a great capstone to the event. And thanks, Tony, for hosting that conversation, which became longer and really more in depth, and was a great sort of discussion of the team sport that is the science and technology development we've been talking about for 2 days, the research and development work that you've done for so long in the lab, Professor. And also, thank you, Stan, for talking about the need for America to take back the mantle of manufacturing. And I know that you co-chair the board at New York BEST, the Battery Energy Storage Technology Center in New York. Bill Acker, the CEO, was actually here today with us on a roundtable discussion. And we've been working with him for 4 or 5 years now to try to build a bridge between California and New York and really drive that manufacturing agenda. And hopefully with the new Biden administration, we will be able to get some mojo from the federal government to support that. So with that, thank you both. And I'll just